So somebody just gave me an idea, and I just made this within the last hour. It's just kind of fun and cute, so I thought I'd share it with you. I just grabbed a cork and a bottle with some hose, little balloons, and if I seal the cork in and try to blow the balloon up, I had a similar demo to this last week. It's hard to, because the air inside is contained and sealed. So as I increase the pressure inside the balloon, it compresses the air inside the bottle, and that fights me. So I'm going to loosen the cork a little so that it's atmospheric pressure inside, and I can't compress the air inside the bottle. Then I can blow it up. Then I seal it, and it'll stay inflated even though it's open to the atmosphere. The air in the room is holding it open because now there's less pressure inside. Well, then you can have kind of fun with it, because either hose, like the one to the red, I can blow up the red balloon, let's see, maybe if I do it this way it'll, well, it worked the first 10 times I tried. Hold on. Let's try that. Wait. It was sticking, I think.
Did you do both at the same time?
If I tried to do both at the same time now, it's sealed, and I wouldn't be able to blow them up because they're compressing the air. But if I try to blow the blue one up, anyway, so when I blow the blue one up, it compresses the air, but that pushes the air out of the red one. Now I can lower the pressure in my mouth and pull the air out of the blue balloon, which decreases the pressure in the bottle, and the air in the room can fill up the red balloon. Pushes in. Then I can blow the blue one back up and then pull it back out. I don't know what good it's for, but it's cute. And you guys understand how it works now, so you can make one at home. I thought I'd share it with you. All right. Today, we get to start heat and temperature. So I like to start this one out with a bang, sort of. So I'm going to pour some cornstarch on this piece of paper. That might do it. Then I'm going to roll it up. And background story. Cornstarch is not flammable. You can make a pile of it, drop a match in it, it doesn't burn. I just don't like making burn marks on the table, so you have to believe me. I grew up in Kansas, and we had grain silos. And it was a big danger. I remember one day my father worked near one, and long story short, it exploded. And you could hear it for miles and miles and miles around. People could feel it, the pressure wave. What happens is the dust, the fine grain dust, you can try this with hot cocoa mix, lycopodium powder, cornstarch, powdered sugar. It doesn't burn, because you can't get enough surface area to volume ratio. But if it spreads out and fills out the container, now you can get at all those surface areas. Each of the little grains is exposed, and that can burn. And so people have to worry about making sparks, let alone smoking cigarettes around such things. If you have static electricity building up and you make a little spark, and it's enclosed with fine powder that's dispersed, you can get a big flame. You guys might enjoy Googling. There's some fun YouTube videos. The Mythbusters even did this. They took some sawdust, real fine sawdust, made a cylinder, and they blew it out really fast so it spread out. And then, of course, they ignited it. Let's do it. All right. It'll spread out this way and should not reach the interpreter. If you're going to try this at home, do this outside. And what I learned the hard way is breathe in before you put your mouth up to it. Cornstarch is really nasty when you get it in your mouth. So. Fun, huh? So if that were enclosed, it would heat up, do work on the surrounding gas. Work, a transfer of energy. It's going to expand. It's going to increase the pressure. And if it's too great, something gives. And that's like the grain silo. Boom. And it explodes. I think it's more fun seeing it than making something go pop. But you guys can do what you want. So that's my cornstarch flamethrower. And we're going to discuss a difference today between temperature and heat. You've heard of both terms, and you still get cornstarch in your mouth. Yeah. And that's what we're going to do. The beginning of the chapter, 15, is that the right? Yeah, 15, starts out with a sparkler. But you guys seen these? You can ignite Bunsen burners with them and make lots of sparks. The sparks don't hurt you. I mean, don't put it in your eye or anything. And he uses it as an example of the sparks have a really high temperature. They're hot, but they're so small. The amount of molecules that have that energy is very few, so it doesn't transfer much energy, much heat. So we would say it's a high temperature, but it doesn't contain much heat. Solids, liquids, and gases are made up of atoms and molecules, particles. And so I got this little doodah. Sorry. Let me focus and get out of the way a little more. Oh, you can see it with the lights on. So let's start this thing vibrating. You can think of this as any substance, like these molecules are a gas, liquid, or even the atoms in a solid. And you can think they're going to have a temperature. If they have a temperature, then they start moving. Each of these is a little object with mass. I know why this isn't working that well. That should be better. There we go. Doesn't sound so bad. That's what's happening. Anything that has a temperature, they're wiggling and moving. Think of the air in the room right now. Air particles. They're wiggling and jostling. If you heat them up, what do you think they start to do? They move faster, yes. And they start pushing on the box greater and greater. And that's a pressure. Every time these balls exert a force on the wall pushes back, Newton's third law. And instead of dealing with the individual microscopic particles, we just say in general, they're exerting a force over an area. That was pressure. So as you heat something up, they push on the walls more and it increases the pressure if it's enclosed. But they wiggle around more. If you cool something off, they have less energy. What's the energy associated with motion? Forgot already? Thank you, Rachel. Kinetic energy. Kinetic energy, 1/2 mv squared. Still applies, but we don't like dealing with the thousands and millions of little particles microscopically. So temperature is a measure of atoms and molecules' average translational kinetic energy. and I'll explain that more, but it's basically an average, a measure of how fast they're moving around. So if somebody's temperature is lower, colder, they have less kinetic energy and they're not moving as fast. But they're still moving. And if it's a higher temperature, they're moving even faster. That's what temperature is. Does that make sense? Since I have this, I want to show you this too. If you put a lid on something, or now we're in a container that can expand. It's not rigid. It's flexible. So if we increase the temperature by adding more energy into the system, they start wiggling around more. They push more. The pressure increases. And the box expands. Like if you heat up a balloon. You can cool off a balloon. It'll get smaller. We might do that later. Okay. So that's molecular motion. That's what the particles are doing. Whether they're atoms, molecules, the diatomic molecules, or big molecules. They have lots of motion. There's lots of energy with them. They can, we call it translational kinetic energy. That's when the whole thing moves. That's what we're used to, when things move in a straight line. That's translational kinetic energy. But they can also have rotational kinetic energy, as well as vibrational kinetic energy, bouncing back and forth. That's just with two. If you had a more complicated molecule, they can translate, they can rotate, and they can vibrate. Those are all forms of kinetic energy. They're motion, but they specify the three types: translational, rotational, and vibrational. It also has potential energy. There's energy stored in the bonds between the electrons and the atoms. And if you break a bond, you can release energy. If you put energy in, you can make it form bonds. And so that has potential energy as well. So pay attention to this part. Temperature is a measure of only the average translational kinetic energy. That's important. I'll write it down. So, as you saw over here, if you just looked at one of those particles, at any given time, it's moving faster and then slower, up, down, left, right. It keeps changing, and the other ones are doing likewise. So, one individual particle could have a whole lot more kinetic energy than another one. But on average, we consider the whole thing, like the temperature of this on average. So we look at all the particles, or all the air in the room. So average is important. But remember, the individual ones can be doing separate things. That's how evaporation occurs. Evaporation is converting from a liquid to a gas. You know, when you're boiling your water and it turns into steam. The ones on the surface are bouncing around like that. And if they have enough energy, they can escape. If they have enough individual kinetic energy, they can escape. And now they're water vapor in the air. But one that's slower, falls back down into the liquid. Translational, it's only that linear motion that matters. And it's the kinetic energy, not the potential. That's what temperature is. And we measure that with thermometers. So I have a few up here. Your traditional thermometer, you guys are probably used to. They used to be made out of mercury. Now we use them with alcohol usually. And most thermometers that we deal with work with expansion of the fluid. When it heats up, as you saw there, they start moving faster, exerting greater pressure, and usually spread out a little. Most materials spread out when they heat up. And these little bulbs down here, if that's what happens, it's the only place they can go is up to the little hole they make. And so as the temperature increases, they expand and fill the column. And if you calibrate that, you can make it the temperature. Alcohol does the same thing, but it expands at a different rate, so you have to calibrate it differently. Here's an old thermostat they recently took out of our building, our area. It has mercury in this little vial. Tips back and forth. Mercury is conductive. It allows electricity to flow through it. So when it's tilted one way, it makes the connection between one side, turns on the heater or the furnace or whatever. But if the temperature changes, it expands or contracts and shifts, physically moves, so that it's either not making a connection or it is making a connection. So again, an expansion moves it, makes a connection or not, and that turns on and off your furnace. It's clever. They're still in buildings. They try to replace them now, which they did, but the plumber was kind enough to give me these. I have a jar of mercury back here that I keep protected. This one and this one are a little different. They use electricity flowing through different metals. They have different resistances. Electricity can flow through them, but at different rates. It's kind of like fluid through a tube. If you make the tube smaller, there's more resistance. It's harder to get through. It'll still go through at the same flow rate, but it's like it's meeting resistance. And depending on the types of metal that you send it through and that resistance, you can calibrate them. This is called a thermocouple, and it reacts quickly. So you can put it in something and you don't have to wait 10 minutes for it to come to equilibrium. Same idea with one of these. This is just old school. This one is kind of a makeshift, uncalibrated one. I just dyed some water green, and what I did was I heated up the bulb. I got it warm, so the air inside was warm. Then I turned it upside down and stuck it in the green water. As the air cools, the molecules slow down, the pressure drops. If the pressure is less inside the bulb, what happens? I'll specify. The pressure inside the bulb is less than what? Atmospheric pressure, which is still out here. So there's a difference in pressure. Differences in pressure make a fluid flow. And so the air in the room pushes down on the green water and up the tube. And so as that cooled, it filled it up that far. And remember, the height of that fluid tells us how much pressure is down here. That's the difference in pressure between out here in the air and in there. Because that's how much it can hold up. So you can turn this into a thermometer, though. If my hand is warmer than the bulb, then I can place it on there, and look what happens to the green fluid. If we play Karate Kid, I'm dating myself now a little, with that movie, remember, they do this. You get your hands warm. I can heat up the bulb and the air inside, because my hands obviously were not doing it zesty enough. Let's try that. And it goes down. Because I heat them up, they speed up and increase the pressure in there and push it down a little. But you can use that as a thermometer then, as this guy's temperature changes. And this one's cool too. Anybody have one of these? They call them a Galileos Thermometer. Anybody seen these? A couple of you? These are just floating balls in a fluid. So it's density and buoyancy. I love the connection between our last unit and this, because each of these balls is contained, and they have a little bit of fluid inside. And if the temperature of this fluid, this ball, increases, what will this fluid do? It's going to get hotter and warmer. They're going to move around faster, and so it will expand. Maybe to here. I'm exaggerating. What does that do to the density of the ball? How does it increase it?
The pressure inside is increased and it's contained within the same volume.
Yeah, good points. You are correct. This expands, increases the pressure here, smushes the air. There's less air in this ball now. That increases increases the density. Because the airspace, which is less dense, takes up less space now. It's like you're filling this with more mass. It doesn't change mass, but it's taking up more space. It's changing the volume. It's like you, when you were swimming. If you take a big breath, you have more air inside you in a space, and it's easier to float. But when you let your air out, your lungs collapse a little, the space is smaller, you become more dense, and you sink, or it's easier to sink or stay down. That's what happens with these. So as the temperature changes, they drop. And when the temperature cools, they float. And the way you read one of these is they calibrate it so the lowest floating one tells you the temperature. But it's kind of neat, just from density and buoyancy.
So in my mind, I would think that the water or the fluid inside decreases in density. I would think that would be like equal to the increase in density of the air. And so I would say it stays the same. So is that not proportional at all?
Those two, good. I was hoping somebody would notice. Two effects are going on. The fluid expands, which would decrease its density. But this contracts and increases its density. And the net effect is the air has a greater change. And so the whole sphere, that effect dominates in what we just said. But you're right. And that brings up a good point. What if the glass of a thermometer expanded at the same rate that mercury did? What would happen when the temperature increases? What's that? It would stay the same. Because the glass would, we'll exaggerate, gets bigger, but so does the mercury. And they move together at the same rate, same volume, because if they were expanded at the same rate. And so it'd be useless. So it was clever that they found mercury in glass. Mercury expands easily with temperature and glass doesn't. But technically glass expands a little bit. So at some point they become, depending on how accurate you need to be. Is that my, and the last one. Infrared thermometers. We're going to talk about radiation next chapter. It's a form of light. Anything that has temperature gives off radiation, safe radiation. It's in the infrared range. It's heat, body heat. You know this, if something's hotter, it gives off more. It has more energy. Well, this can pick up the infrared. There's a sensor inside that the heat from your body comes at it. I aim at you. And it registers it, and they calibrate it to tell me the temperature. They're very clever. They started them with, doctors when they stick them in the baby's ear, That's what they're doing. They're measuring the heat given off, radiated from your eardrum. They learned that's a good indicator of your average internal temperature. And the sensor calibrates that and gives you your body temperature, but really fast. That was really clever. Now they have ones that measure your temporal artery or something like that, and they just run it across. Same idea. It's measuring the energy, the heat energy you're giving off. Okay. Scales. We have two main scales in the United States. Celsius, last name of a scientist, and it is 0 to 100. When you say degrees Celsius. That's how they calibrated it. Temperature means nothing unless you give it a reference point. So, historically, they said zeros where what freezes? You know? Yep. And 100's where it boils. So they marked those off, divided it up into 100 divisions, and said, there we go. That's the Celsius scale. We call it Celsius now after the scientist. But historically, Brian, here's your question when he starts looking. It was called centigrade. This thermometer actually says centigrade because centi is like centimeter. It means 100 or 100th. You can divide it into 100 little divisions in grade scale. So this is the same thing as a centigrade scale. But now we call it Celsius after the scientist. And in the United States, us slowpokes that won't change. What does water freeze at? 32 degrees. And boils at? Good job, 212 degrees Fahrenheit. Another guy's scientist's last name, but same concept. One advantage of Fahrenheit is there's more divisions in here. So this is actually a little more accurate because one change of a degree is a smaller resolution in Fahrenheit than it is in Celsius. But the rest of the world uses this and we still linger. There is one more. Anybody know what it is? Good job. And again, the last name of another scientist. This one's not based on freezing and boiling. It's based on energy itself. And so it goes from 0 to infinity. And it's just called Kelvin. We don't say degrees Kelvin. So for freezing, since I got these here, it would be 273 to 373 Kelvin. That's where water freezes and boils. Absolute zero is what we call it at the very bottom. And that's based on when an atom or a molecule has no more available energy to give up, kinetic energy. So back with temperature, an average translational kinetic energy. If the thing cools down more and more and more, eventually you think it would stop moving. It can still be moving some things at absolute zero, but it has no more energy that's free to give up. And as we mentioned once briefly in this class, nobody's ever been able to attain that yet. They got really, 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 really close. But that's the reference point. When something has no more kinetic energy to give up, that's the 0 point. Can you tell what value that would be in Celsius? That's equivalent to negative 273 degrees Celsius, if you convert it. Absolute 0 here. And then it has the same divisions as Celsius does. That's convenient. And so if you go up 100 from freezing, let me back up. Make sure you guys got this. So 0 degrees Celsius is 273 Kelvin. Do you see that? Because you come up to 0 from this, and so you'd be at 273 higher. And then you add 100 and you're at boiling water. These are used in science when we're doing thermodynamic equations. That's the standard unit in physics, the Kelvin. But most of the world uses Celsius. These make sense? You're familiar with most of it, most of your life. I won't make you convert back and forth between Celsius and Fahrenheit. Okay, now you know the scales. I hope you know what temperature is by now. So what the heck is heat? Anybody want to take a stab? You had to explain to your mother right now. I think heat is. Tell me something you know. Molecular motion? It has to do with that. Good. Let's build on that. Transfer of energy. Yes, that's a big component of it. And what type of energy? Does it transfer? Yeah, usually kinetic. The energy can go into different forms. You know, if you put this molecule on your stove and heat it up, we say, right? That means we're transferring energy into it. And it can absorb energy. And it can go into different forms. It can cause it to translate more and increase its temperature. But it can also be absorbed into this molecule, but just make it vibrate more. Would that increase its temperature? Temperature is a measure of average translational kinetic energy. So if energy goes into a molecule to make it rotate, its temperature does not increase. Or to vibrate, the temperature doesn't increase. Or to break some bonds, melt ice. When ice is melting, what temperature does ice melt? At 0 is that transition. If it's cooling, it starts freezing, 0, and if it melts, it's 0. But I don't know if you realized, if it comes up from -2, -1, 0, it starts melting. The ice stays at 0 degrees Celsius until it's melted. But you're still putting energy in. Where does that energy go? Not into translational kinetic energy, because it doesn't increase its temperature for a moment. It's a phase change. It's changing phase from from solid, ice, to liquid, water. It's going into breaking up the bonds, the potential energy. That's why you don't see the temperature increase. You follow me? Same thing happens again when a liquid boils and turns into steam. That occurs at 100 degrees Celsius, right? Well, the water will not get above 100 degrees Celsius, even though it's boiling. Because it takes energy to change those bonds and create it to steam. Once it becomes steam, now the energy can go into translating it, speeding it up, and its temperature will go up. Kind of looks like this. Let's draw it. If that's temperature, and this is time, we'll call this 0 degrees Celsius. Then if you have ice, and you're putting heat in, it's on your stove. It comes up, it gets to here, and it has to melt first. But its temperature does not change, it doesn't increase. But energy is still going in. And then water. Once it's turned into water, it now can increase its temperature. And then the same thing happens up here with steam. So here it's changing temperature, here it's changing temperature, and here it's changing temperature. Here and here it's not. But you're still adding heat, transfer of energy. It's just not going into average translational kinetic energy. I know some of you are going, you're really redundant today, Adam. But this is on purpose, because that's one of the distinctions between temperature and heat. Temperature is only a measure of average translational kinetic energy. Heat is the transfer of energy, energy in transit. And the second main point with heat, heat will only flow when there's a difference in temperature. You know this. If you put your water, this isn't water, but you know what I mean, on your stove, and they're both at room temperature because you haven't turned on the stove, they're at the same temperature. There's no temperature difference. No energy will flow one way or the other. But you turn on the stove and it gets hot. Now there's a difference in temperature, and so energy can flow. That's heat. Heat is energy in transit. It's a lot like work. Do you remember how work allowed us to change from one form of energy to another or relocate it? Increase or decrease kinetic energy or potential energy? Works just like heat in that sense. We don't say an object possesses work. This possesses work. No. It has the ability to do work on something or to be worked on. Likewise, we don't say cornstarch contains heat. That's important. We don't say matter contains heat. What it contains is energy. And we can transfer that energy. We can say it has a temperature and thus give a measure of its average translational kinetic energy. But we don't say it has heat. So I'm going to try my hardest to always refer to the total energy something contains. It's its internal energy. Some people refer to it as thermal energy. What they're referring to is all the energy, not just translational, but also rotational, vibrational, and potential. All of that energy is internal to that matter. That's what something contains. And if you change some of that, then heat had to flow out or in. And sometimes that can change the object's temperature, but not necessarily. It depends on if it's changing phase or not, right? Still with me? Good, good. Where are we at? If you have an object and it's hot, you have an object that's cold, so we could say that means the temperature is high for that one, and the temperature is cold for this one. You probably know this. Which way does heat flow? From cold things or hot things? Yeah, I heard most of you say it flows from hot to cold. Heat in physics is given the variable Q. And so we can say that heat flows from hot things to cold things. That's a law of thermodynamics. Naturally, if there's a difference in temperature, energy will transfer. Heat will flow from hot to cold, not the other way around. What do you think you'd have to do to transfer heat from something cold to hot? What'd you mouth?
No, it's not right.
If naturally it wants to flow this way, and you want to force it to go the other way, what do you think you have to do to the system? You'll have to do work on it. You'll have to put energy in. Like a heat engine. If you want to force something to heat up, you got to put energy in. It's conservation of energy. Well, you can't get it for nothing. But it will like to flow downhill to equilibrate, to come to equilibrium. If these two are in contact, you know what will happen. Eventually, what temperature will they become? something in between. Yeah, this one will cool down because energy is leaving it, and this one will absorb it, so it'll increase until they come into equilibrium and they're the same temperature. And that's all a thermometer does. That's all it can do. This bulb right here comes into equilibrium with the air in the room. And so it's great at measuring big things. But as your book says, what if you put one drop of water on the bulb? Boink. Now there's let's say one cold drop of water on it. Well, the thermometer will be hotter than the cold drop of water. So the thermometer will give up some heat, some energy, and the cold water will absorb it. That affects the thermometer. That's essentially how it works too. That's how they measure it. It's at coming into equilibrium when heat flows. And heat will only flow if there's a difference in temperature. Let's ask you a few questions. So clicker time. And let you go. All right, the session ID is up, so while you get your stuff out and log in, I want to remind you, because it's posted online, we've started chapter 15 today. Next week, we will finish chapter 15, and I'll start and cover 16 throughout the whole week. So we'll be doing heat and heat transfer. Then you guys get spring break. I decided that normally I'll finish covering the material before spring break, but instead of forcing you to turn in your homework on that Sunday like we normally would, why? I don't need it yet, so you can have more time. So you'll have all the spring break too to finish it up and study. When we come back from spring break, that Sunday is when your homework will be due. We'll review this stuff because you'll have forgotten some of it, right? All right. But this next unit is chapter 15 and 16. I'll spend a couple days on each one. But the way we're going, we should finish it before spring break. But I won't give you the test right when you come back. I always hated that. So. Okay. Polling is now open. Yes? So what were you doing? I had it up so you guys could do it. The number is 872-133. 872-133. Polling is still open. 872-133. So I want to see if you can reason. I know I just exposed you to this, although in theory you all read it and studied it before you came to class, right? So let's see. If you have twice as much molecular kinetic energy in 2 liters of boiling water compared to 1 liter of boiling water, you do. You have twice as much because there's twice as much material. What will be the same for both, though? Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Meh. All right, over half of you think temperature will be. And some of you think thermal energy will be. About a third of you. Thermal energy is that total energy that's contained in it. So discuss it with your neighbor and I'll let you revote. Is it just temperature Or is it both? That's what the majorities is voting for here. They either think it's just temperature is the same, or maybe the thermal energy is the same as well. Let me reopen the polling as you discuss it. You can revote. There's twice as much of one than the other. But they're both boiling. So most of you agree that the temperature is the same. I'll give you that. That's correct. Because they're boiling. But does the 2-liter one have more internal thermal energy? Yeah, that's what I want to see, if you've changed your mind or not. Each little individual particle, temperature, is a measure of its average translational kinetic energy only. Individual ones, on average. But they might have other forms of energy. And what if you have more of them? Does that matter? 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay, a few more of you swayed to answer A, which is the correct answer. The individual molecules have a certain temperature. So on average, they all have the same energy. Do you agree with that? But what if you have twice as many of them in the 2-liter? Then the total energy is twice as much because you have twice as many of them. Let's put some numbers to it. This one has 2 joules of energy. 2 joules, 2 joules, 2 joules. Well, so do these. 2 joules, 2 joules, 2 joules. But there's 200 of these and only 100 of these. So do you see that the total would be more? That's what we're talking about with total internal thermal energy. Okay. Polling is open. So 2 bodies, one's hotter than the other. The hotter one has more, what we'd say? 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Oh, kudos. Majority, yes. Temperature is the average translational kinetic energy. That's telling us the individual particle's kinetic energy. Good. That's temperature. Temperature. And there's one more I wanted. This one. Polling open. Then I'll stop. You got a hot, glowing, red-hot thumbtack. It's small. Throw it in some warm water. Which way will heat flow? From the tack to the water, or to the water to the tack, or it doesn't matter? While you're deciding, who has more thermal energy, internal energy? Do you think? The little red hot tack? Or let's say it's a huge bucket of warm water. Good, the warm water, because there's a whole lot more of it. So the total energy is more. But the tack is hotter. It has a higher temperature. Which way will heat flow? 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Oh, bless you. 91% of you. The amount of energy does not determine which way heat flows. Temperature does. Very good. It always flows from something hot to cold. I hope you guys have a great weekend.